Welcome back, everyone. Today we're going to consider the conditions under which we can use Newton's laws alone to solve for all the forces in a body that's in static equilibrium. So we'll start by considering a structure like a pin-jointed truss that's in equilibrium under load. So what we mean by a truss, a pin-jointed truss, is a structure like this with discrete elements, and at each of the joints or nodes in that structure there is a connection that transmits forces but not moments. In other words, these joints are free to rotate if they can, but they transmit forces. We will also have loads acting on the structure and reaction forces, in this case at the ends here, where the structure is constrained. So the question here is, can the equations of static equilibrium be used to solve for the forces in this structure, specifically in each individual branch or member of this truss? So the answer to this question depends on whether the structure in question is what's known as statically determinate. This requires, in general, that the number of unknowns in the system in the analysis is equal to the number of knowns, which will be the number of equations that we can obtain from the force and moment balance laws. Now, in the case of the pin-jointed truss, these pins can't transmit any moments, so there are no moments. So for each node, for each pin in this structure, we have two equations, being the two force balance equations. We can therefore write two equations, being the force balance equations, for each of the nodes in the system. But any part of the system that is constrained, in this case the ends, will have corresponding reaction forces that are unknown. So we have equations at every node in the structure, two equations at every node, but we also have some unknowns, in this case two unknowns being the reaction forces at the ends. So we'll call the number of knowns 2n, where n is the number of nodes, and the number of reactions to be r, so that the net number of knowns in the system is 2n minus r. There are also m elements of the system, m members of this truss, that carry forces, and the force balance equations allow us to relate the forces in the members to the forces at the nodes, to balance them at the nodes. Therefore, this system will be statically determinate when the number of members of the system, m, is the same as the number of equations minus the number of unknown reactions. In other words, m is equal to 2n minus r. So let's start by considering a simple example with just 4 nodes. You can see here. And so therefore we have 8 equations. But there are 2 unknown reaction forces, each with 2 components, at the ends, here and here. And there are 4 members. So therefore 2n minus r is equal to 4, and m is equal to 4, so this system is said to be statically determinate. The equations of equilibrium from Newton's laws alone, the force balance equations, since we don't need moment balance equations, are exactly enough to solve for the forces in every element of this structure, which is indeed static. So now let's consider a situation where we still have the same number of reactions and the same number of nodes, but we have an extra member, and notice as this second member crosses over, there's no node connecting that with the original diagonal. So now the only thing that's changed is we still have 2n minus r as 4 pieces of information, but we have 5 bars in which to solve for forces, and so there are more unknowns than there are equations to solve for them, with the result that this system is not statically determinate. It is static, but many solutions are possible. The system is stable, but indeterminate. In other words, we need additional information before we can solve for the forces, before we can partition the forces between those two diagonals. There are many possible different solutions, and some extra piece of information is needed in order to resolve that uncertainty. And so this is normally the way it is in continuum mechanics. Normally we need additional information, and that additional information is something about the specific properties of those materials, so that we can understand that as it tries to deform, that the loads will change and they'll reach some new equilibrium based on additional information. So here's another case where now we've taken away the diagonal. So again we have 4 nodes and 2 reactions with a total of 4 pieces of information. But now we only have 3 pin-jointed members. And because they're pin-jointed, this structure can keel over and rotate. And as such, it is not in static equilibrium, and it's not even in equilibrium. It's not static. This kind of structure, unstable structure, is called a mechanism. So the basic idea about a statically determinate system is that the number of equations that Newton's laws gives you must match the number of unknowns. And when it does, then we can use Newton's laws for bodies in static equilibrium to find all the forces in that system. But often that's not the case. Sometimes it's not the case because the system's simply not in equilibrium. But if it is in equilibrium, it could still be indeterminate. There could be more forces, unknown forces, than there are equations from statics alone to get an answer. And in order to go beyond statics, we need more than just Newton's laws that we used in statics. We need information about the mechanical properties of the system, and that's normally the case in continuum mechanics. So in the next class, we'll do some examples where we apply statics to statically determinate systems to solve for these forces. But after that, we'll have to introduce additional information about the material properties of the system before we can get an answer.